So today, to take a short break from constructing the boards, I wanted to talk through a little bit about the software that I've been using to design and test these boards, because for the amount of money that it actually costs, I think it's very good value for money, and it has certainly helped me design my previous project, which was a 74 series TTL based 6502 computer. That was a couple of boards as well. These boards, well, those boards back then were a lot less complicated. The software back then, although it was very functional, it didn't have quite such as good options for PCB layout and automatic routing. The software, since I created the 6502 clone boards, has upgraded their routing software a lot, has upgraded their software with respect to automatic layout, but also simulation. So the software I'm going to show you has allowed me to transcribe the original bomb jack schematics that I found in a PDF file, and to change the operation of bomb jack hardware from ROM-based static graphics to RAM-based graphics, and also adding a whole bunch of extra functionality in terms of rendering larger sprites, but also adding extra functionality in terms of what's called a Mode 7 layer. Mode 7 was a technique for scaling, transformation, rotation, mirroring, or flipping screens, or a screen, on the Super Nintendo. It basically looks really cool, especially if you're thinking about retro machines and retro games. It was a technique commonly used to render 3D road surfaces and perspective road surfaces anyway. So this is Proteus. It's made by Lab Center, and as you would expect, the properly registered version, depending on the license you want to buy, can give you access to more gates or connections or more ICs that you want to simulate on your designs, or say, for example, if you wanted to simulate certain types of processors or displays or USB based devices. It's got a whole range of license models. So I just have the license that allows me to build very large projects. It does not constrain me in terms of netlist size and the number of pins, because I have the open-ended license. When I was designing the original processor, 6502 74 series boards, I actually found that I very quickly reached the first limit after the initial software. I think it was probably around about 500 pins or something like that. And I was trying to design the boards so that it would be split apart and I could test them in isolation, but then I just bit the bullet and I bought the next license up, and then the project grew again, so I just bought the next license up again. And then I wanted to have things like the virtual logic analyzer, so I bought the next license again, and so on and so forth, until I got to such a large state of project that I just bought the open-ended license after that. So when I found the original bomb jack PDF, a friend and I were debating on how the bomb jack hardware actually worked. I was saying, look, all of these ICs, they're going to be doing all of your display logic and processing. And a friend was going, well, yeah, but how? So I went, well, hold on, I'll start inputting the schematic into this simulation software that I've got, and I'll see, because it's all very well and good looking at what are obviously hand-drawn schematics from the original Bomb Jack arcade hardware. But the real proof of the pudding is actually simulating it or building it or simulating it. Now, simulating it is a lot easier than building it, so that's what I decided to do. So the original Bomb Jack PDF has, I think it was around about 8 pages. And so when I was transcribing originally the PDF, I would transcribe page 1 of the PDF to the first sheet, and then the second page of the PDF to the second sheet, and the third page, and so on. That was initially. I wanted to do that because I wanted to try and make it easier for me to double check all of my inputs for the schematic, and I wanted to make it easier for me to refer back to the schematic. The original plan was to create a board or two which operated identically to the Bomb Jack hardware, so that I could actually prove that it was entirely possible to reverse engineer working PCBs from the schematics. However, after that, then I really got interested in designing bigger and better functionality. I wanted to add all sorts of extra sprite capability. I wanted to add scrolling backgrounds, pixel scrolling backgrounds, for example, whereas the original Bomb Jack PDF did not have scrolling backgrounds. And also I wanted to add things like mode 7 and scaling and all sorts of stuff. So this is what I did. So anyway, so sheet 1 basically contains all of the logic analyzers. These are the logic analyzers here. They contain the digital data generator. Now if I zoom in on the digital data generator, it outputs a whole bunch of stuff to it, like the virtual memory interface, the virtual data bus, if you like, which is data bus bits 0 to 7, the extended memory data bus, which gives us access to all of the RAM that I added to replace the ROMs, and then we have 16-bit address bus and memory write. We also have inputs for the VBlank. We also have inputs for the horizontal clock signal, the pixel position basically. It is 9 bits because the screen is wide. However, the rendered screen is 256 pixels by roughly 256 pixels. However, there is horizontal overscanning for the borders and the flyback period, etc., etc. And then we've got the vertical pixel, or raster line, if you like, which is 8 bits wide. These on the right here are inputs, because the digital data generator actually reads a whole bunch of expected, but it waits for expected triggers from these values on the input, and then it will output one or more bytes based on some textual definition and also some binary data files and stuff like that. This is actually not part of the standard Proteus simulation suite. It's actually an additional virtual device that I actually created because I wanted to make it easier for me to generate debug patterns to feed into the whole simulation, but I also wanted the ability to record. So this actually allows me to record or to play back, and this one plays back information from the testdata.txt file. It allows me to define text-based format. This virtual display device is the main proof of concept for the simulation. It's the main proof of concept for the simulation. So it takes in vsync and hsync from the simulated hardware. It also takes in 4 bits of blue, green and red. Actually, it can take up to 8 bits of red, green and blue signals. But for the simulation, the actual bomb jack hardware itself only uses about 4 bits worth of colour. So we just leave it at that for now. I also have some debugging information for the horizontal and vertical pixel clocks. There is also some rudimentary address decoding here. This basically asserts that if the first or 0th bit of the extended memory bus is high, then it will allow me to start addressing the RAM, which was the original RAM on the bomb jack board, but also some of the extra RAMs that I've been memory mapping into this space here. Mostly control registers, but there are also some screens for the character screen. There's also some color screens and other such things like the Sprite control registers and things like that, which are all within this memory map space here. And also I think the mode 7 registers are also mapped into this space as well. All of the extra Sprite information, all of the extra character definitions, all of the extra tile definitions, all of the extra tile definitions for the mode 7 screen. Whereas on the original bomb jack, with the exclusion of the mode 7 screen, which wasn't in the bomb jack hardware, all of these were originally ROMs, and as I said, I wanted to make them RAM. So I mapped those to different extended bits in the extended memory bus register, if you like. Effectively, it means that we have the 16-bit addresses that would have come from the CPU, plus 8 more bits, to give us a whole bunch of extra memory. So basically up to 24 bits of extra mapped memory, if you like, approximately. So there's also a little latch here for the vertical position. It's actually not excluded from the simulation, but it's excluded from PCB layout. It's because this was just feeding into this here. It basically allowed me to remove any potential for clock ripple, because the inputs here were potentially rippling around a little bit from the clocks, because actually it uses clocked counters, 4-bit counters, to generate the horizontal and vertical pixel clocks, and we'll see that on the other sheets. So sheet 2 and page 2 on PDF. So the PDF actually contained dip switch logic. It didn't contain really much else. So actually what I did was that I populated this sheet with a whole bunch of headers. These headers go on to the different boards. I created expansion bus A2, A3 and A4, and row and column. So all of these, when you look on the PCB layout, these are the, if I turn off the rat's nest view temporarily to make it easier to see, these are the standard memory bus headers, basically here on each of the boards, and this is copy pasted in terms of layout to all of the other boards too, to make it easier for me to stack the boards or to interface the boards consistently. And we can see here that on these boards, you can see the relative sizes of them. This top left board here is the video board. Then we have the character board here, which is this board here. This is the character board. Then we have the bigger Sprite board. And then we have kind of like, it's smaller than the Sprite board, but it's bigger than the character screen board. This is the 16 by 16 tile board. And then this is the mode 7 board, which is the largest board out of the 5 of them. And to keep the layout nice and easy for me to design and think about and solder, I actually have placed manually some components. I especially wanted to make the video output nice and neat. I also wanted to make my resistor ladders nice and neat. I also wanted to ensure that these memory chips were placed roughly in the center of the Mode 7 board. I found that when I did this, it really helped the auto placement and the auto routing. And also, similarly for the Sprite board, I wanted to make sure that my Sprite scanline logic, and we'll get onto the Sprite board and how it works in more detail, but I wanted to make sure that the Sprite logic with its pull-up resistors, because it stores inverted pixel values to aid in having a nice quick pixel test. I wanted to make sure that all of this was placed consistently, so then I could let the auto placer then more easily place all of the other components around, but also I wanted to make sure it was nice and neat for later soldering purposes as well. I also wanted to make sure that the auto placer understood that I wanted to have a nice balance of the board in terms of placing the components for one half of the Sprite logic and then the other half of the Sprite logic. Because the Sprite logic, when it renders, it actually renders alternate scan lines as it's rendering the pixels to the output video. But then it switches over and then it starts calculating Sprite pixels on one scan line and as it's actually outputting the other scan line, and then it flips all of the logic around and then it does the other half. So we actually have two scan lines, one being updated and then the other one being output to the video, alternating in that fashion. It's actually a very efficient use of memory. It means that you do not need to have full RAM for two screens. You can just have two scanline buffers. So we'll go back to the original schematic here. And this is root sheet 3. Now root sheet 3 corresponds to the BombJack PDF page 3. And this is mostly to do with video timing, and the horizontal and vertical video signal generation comes from here. So what we have first of all is that we have some analog circuitry here for generating a 12 megahertz approximately clock using a crystal and a couple of resistors and a nice capacitor. And this is jumpered, so it allows me to either select the clock crystal output, or we can use here a CAN oscillator. In the built boards, it uses the clock crystal arrangement. And actually I've tested this and it works really well. So the whole clock signal comes looping through this little hex inverter, if you like, with some output enable. And this allows the clock signal to come through and then be propagated as 6 megahertz signals, because it comes through and it actually comes through as the video clock signal here. Actually loops around and comes in through this flip-flop here, and then it will circle around like this. So it's actually a very stable setup, but what this does is that this hex inverter generates a couple of 6 megahertz clocks and an inverted 6 megahertz clock as well, which is really useful because some of the timing uses the source 6 megahertz, and then some of the timing, for example, if it wanted to read RAMs or clear RAMs or whatever, then it uses the off cycle or the inverted cycle 6 megahertz clock. So the 6 megahertz clock comes in here, And what we have as an output is that we start getting 9 bits worth of horizontal clocking information here. Interestingly and usefully, the lowest bit, the least significant bit, actually uses the output from the flip-flop, which is as you would kind of expect, because then the next 8 bits come from 2 clocked counters. And all it does is count from 0 to, I think it's 384, and then resets itself. But it resets itself with a certain input here, as you can see. I forget the exact way that it actually works now, but it was documented, but the scanline schedule is actually documented in readme.md file anyway. And basically the line count starts at 180 in hex. It then goes all the way to 1FF hex. And then it loops round from 0 to FF, if I remember rightly. Something like that. So the horizontal signal is used to trigger various the beginning and the end of the displayed screen area. It's used to trigger various horizontal TV syncs, for example. It's also used to trigger the start of the scan line logic for rendering sprites. For example, it's used to trigger when character data, when tile data should start to be read, should start to be processed. So basically we have a pixel being output on every tick of a 6 megahertz clock. And a lot of the logic actually uses very short paths for calculating the output pixel, looking up its color, and then outputting via the paleograms, and then going through some resistor ladders to generate the final output pixel. It's actually a really efficient way of operating. Everything is calculated just in time. There is no screen memory for the pixels, at least not for the original Bornjack hardware. Everything is looked up just in time. And we can see here that this is the horizontal sync circuitry, which basically generates a sync based on the bits for some of the horizontal position register, if you like. Here we have obviously the vertical sync generation and the vertical pixel position generation. And of course, this is not clocked on the 6 megahertz clock. This is actually clocked on 256 being reached on the horizontal position, horizontal pixel position. We also have some extra logic here for generating the V blank signal from, again, the vertical position. And we also have some logic here for generating the comp block signal, which is used internally to schedule some block comparisons, I think, for the sprite board. If we'll get there in a minute, several minutes. And this is generating the TV sync signal, and this is generating an inverted comp block signal, for example. This little circuit up here is actually really important. It generates, depending on the horizontal pixel scan position, and it's not the pixel position, but it's actually the times 2 pixel position. It generates a whole bunch of timing signals, say for example for loading a definition, for loading a color, and then I think this one is for some other internal timing signals as well. I think it's for starting some shifters and stuff like that as well, which basically says I really want to start outputting pixels now. I think that's what it does. We'll clarify that a little bit later on. And this is all based on the pixel horizontal position, but also based on a nice clocked input as well from this. Just to make sure that all of the internal pixel signals are synced properly. Because there are various ways in which sometimes the sprite registers, for example, or the character registers, or the character screen, and the output pixels for the characters and the tiles are delayed by 1 or 2 pixels. This delay is actually, I think, also documented in the Readme file in the raster line schedule section. It talks about having an 8 pixel delay, but there is also a couple of pixels delay as well that I found. The borders, for example, aren't quite aligned. And this delay is there to account for potential delays in reading different RAMs and so on and so forth. I actually found some of these undocumented delays and unexpected delays when I was trying to recreate an emulation of this hardware based in Java, based on the simulation and based on the schematic. But also based on my knowledge that I gained from working on this schematic. But I wanted to have a nice, faster Java-based emulation, and actually the Java-based emulation has all been released, and I'll put a link to that as well, but you can download the whole Java-based SDK, and you can code stuff on it, and you can I've created a little game demonstration as well to show how all of the tool chains merge together. I created a demonstration of how the tool chain can be used to create a small little game, how the image conversion, how the map conversion can be used, how it all ties together, how the assembler can be used, because I included an emulated 6502 along with an emulated memory data bus as well. So all of that is packaged together as a build that you can download and create software with, and it's compatible with the simulation. It actually outputs debugging data signals that can be used by this simulation here from the debug output. So you can actually emulate it in real time, generate your debug files, and then simulate it in not real time in this simulation here using the Proteus software, just to really properly validate that the simulation of the video hardware is aligned with the emulation in Java of the video hardware. So that covers page 3, root sheet 3, in terms of all of the video signal generation. So now we will get into the real nitty-gritty, which page 4 on the PDF, page 4 on the schematic PDF, page 4 on the schematic PDF starts dealing with sprite logic. It's really interesting that they did the sprite logic first, before the character screen and before the tile screen, but okay. This was what my friend and I were really interested in discussing on how things worked. Actually, we were really interested on what appears on sheet 5, which is the dual scan line RAM buffer logic. But even so, this root sheet 4, page 4, is really interesting because this contains the Sprite RAM register access logic, which is up here in this portion of the board. It allows, depending on what memory lines you're asserting from the CPU, from the external memory bus, you can either be selecting the CPU requested memory bus lines if you're doing a write, because it's only writing. There was read logic, but in the original BOMJAC hardware, if I recall correctly, but I stripped out all of the read logic because I didn't really want to have read logic in this version of the hardware, which I am going to interface with other retro computers. I want it to be a simpler write-only interface, because I won't be tying directly into the CPU's memory space directly. I'll be using a more easy to I'll be using an easier to interface memory access system, probably via something like the user port, and I wanted to make it one direction for only writing, really. So I stripped out all the read logic, made it a lot simpler. But basically, if you are writing 9800 in hex, then it switches the data input from the data bus, the external data bus, through here, and then it starts writing data into these signals here, which eventually go into the internal Sprite data bus, ISDB, internal Sprite data bus, which can go to, say, for example, the internal Sprite registers here. If I remember rightly, on the original BOMJAC hardware, the Sprite registers were, I think, maybe being stored in a couple of RAMs. I changed it to be 1 RAM. I'd have to double check on that. But I think that's what I did, because I wanted to make sure it was a smaller, simpler circuit. So if you're addressing the external memory data bus, then it turns off the clocked horizontal pixel position, so it doesn't use that as the memory address. It uses the CPU's or the external memory bus address, and it feeds that through to the address bus on the RAM here. If, however, you are not writing anything from the external memory bus, then all of the memory addresses that it reads come from the horizontal pixel position on the screen. And these horizontal pixel positions drive these horizontal pixel positions, because they drive and get selected through this 2-to-1 selector, 4 of them, quad 2-to-1 selector, based on the input here. These horizontal pixel position values, which turn into the address in the memory that's being read, are synced with the MDL, the VPL, etc., for loading different values sequentially through memory that mean different things. So say, for example, the sprite definition, I think this is the sprite definition one, I think it loads that one using the data that's pulled from memory, which comes through this way. So when the memory is reading, rather than being written to, it comes through here, it reads, the data comes out through here. So it comes out from these signals. It then flows through here. This is a bus transceiver. This was always on, so actually I've just been experimenting now. In version 3 of the hardware, the bus transceivers are there, but I've been experimenting with removing them just to see if it all works. It does. The values from the memory flow through here, and then they come into these here. So what that means is that it loads the sprite definition index here. It latches it basically because it's a 74273. And it loads the color of the sprite here. The color also contains basically the palette index. It also contains things like the what does it contain? It contains things like, okay, so this latches the sprite's palette index. I think the original bomb jack hardware had 16 8-bit palettes it could select. I actually expanded it so that it went up to 32 8-bit palettes that it could select. So instead of a total of 128 colors, I expanded it to be 256 colors, which was a nice useful addition. And this also contains not just the palette index, but it also contains logic which defines whether or not the sprite is full screen in height. This actually just basically turns off the sprite comparison logic in the Y position. It makes it always render the sprite based on its horizontal position. And it also contains horizontal and vertical flip information. The vertical flip is really quite simple. I think all it does is that it inverts the values that it's read from the comparison. If I remember rightly, so this is, I think these are a comparator. I think these are an adder, if I remember rightly, a 74283. I think what it does is that it takes, yeah, these are an adder. So what it does is that the vertical pixel position here and here, in terms of deciding when to start rendering a sprite. How it decides to start rendering a sprite is really quite interesting logic. It takes the vertical screen position, the scan line that it's currently rendering, and it adds it to the sprite position. Now, this is tested by this VPL signal here. This VPL signal, don't forget, came from this timer here. And it's timed to coincide with reading the data from the RAM. So the format for the sprite data is that byte 0 is the tile code, byte 1 is the palette index plus the flips and the full screen sprite, and then byte 2 is the sprite's X position and byte 3 is the sprite's Y position. So as it's timing the read for the sprite Y position, this VPL is triggered. So basically what it does is that it clocks the output of an 8-bit add. Now the sprite position, when it's stored in its sprite register memory, the sprite position is actually, if I remember correctly, is inverted. So instead of doing an 8-bit add, it's actually doing a subtract. And what it's doing is that the lower 4 bits just get clocked straight away and get stored straight away into this latch here on the comparison. But the upper 4 bits, unless the sprite is told to be full screen, the upper 4 bits go through and flow into this latch here. So what that means is that we have some lower 4 bits, because the sprites are 16 by 16 or 32 by 32. These lower values are used to index the current sprite scan line to draw, and the upper bits are used to decide on whether or not this sprite should be visible or not. And this logic then turns on or off the sprite processing for this particular slot in the scan line as it's calculating from left to right in the scan line. It decides on whether or not the sprite data buffer scan line logic needs to be activated or not for this particular sprite, based on this adding inverted subtraction, if you like, from this test here. This is why it was really simple and not much extra work to put in a whole bunch of for extra functionality for using full screen sprites, for example. Whether or not a sprite is whether or not a sprite is horizontally or vertically flipped is again just a simple case of deciding on which signals to invert and when, because the vertical position of the sprite is then used to directly address into what is really interesting, the 3-bit plane sprite data lookup. The reason why it's 3, the reason why we've got 3 things here is because the sprites, characters, and 16x16 tiles on the original hardware all used 3-bit color. That means you have up to 8 colors. Color 0 is always transparent, and colors 1 to 7 come from the palette data. So this is why we have 3 fast RAMs here, here, and here, with memory address line selection logic. Now, originally these were ROMs. So the address logic was always a case of taking the compared sprite Y position and then just using that to index along with the sprite. So the sprite definition index, which was also read from the sprite data, just forms the upper bits of the total address being used for the sprite bit plane memory. So it's a really efficient way of decoding the sprite data that you want to read from memory. Now, because it's bit planes, 1 byte stores 8 pixels. So 2 bytes stores 16 pixels horizontally for a sprite. So what it does is that the whole timing of this is very carefully timed so that the read for the next 8 pixel chunk of the sprites starts at exactly the correct position where it can start feeding into these 3 clocked shifters. Okay, so these 3 shifters will define on how the sprite is horizontally shifted. If you are, or horizontally flipped, sorry. So if you are not horizontally flipping the sprite, then all it does is that it reads in the 1 byte, 8 pixel values here, and then it shifts it out one way, boing, for example. But if you are horizontally flipping the sprite, all you need to do, basically, is to shift the other way, which is what these lines do here, you need to shift the other way and you read the output from the other end of the shifter. Okay? And then what you can do is that once you have this logic, it means that then you can start using either the 3-bit pixel from this end or this end of these shifters. And then you can use that in the next part of the logic. This logic here deals with configuring the hardware to render or start rendering 32 by 32 pixel sprites. So the original BombJack hardware had a really neat feature where you could start rendering 32 by 32 pixel sprites instead of the normal 16 by 16. If you enabled all of the sprites, which I don't think you could do with the current version of the hardware, because, okay, so this stores a 4-bit value for the start index, and then this stores the end value for the index. So what it did in the horizontal and vertical, what it did on the horizontal schedule for the raster line schedule, there was logic that said, I want to be rendering 32 by 32 sprites right now instead of 16 by 16, and there was a little bit of subtle modification of the values that were used from the clocked inputs for the X and Y position, and also the palette index, and also the sprite index to be used. So these little 4-bit latches means that you could set the indexes for 32 by 32 pixel sprite rendering. And what it means is that when you start rendering a 32 by 32 pixel sprite from that particular index, it would basically internally skip over the sprite definition and the palette and the X and the Y position. It wouldn't read those, it would just reuse what had been read from the previous one, but it would continue on with the horizontal position or the vertical position. And what that meant is that the hardware very cheaply and simply could start rendering double size or quadruple size sprites with very little extra logic. This is what this does. This is these are the two comparators, and based on the output from the comparators, it would subtly tweak on whether or not you were using 16 or 32 pixels. It meant that when you started rendering the 32 wide sprites, you would effectively reduce the number of sprites that were displayed for that portion by 2, but double their horizontal sizes. It did not reduce the number of sprites that you could display vertically, because the vertical logic is different. It's based on the scan lines rather than outputting horizontal pixels into a scan line buffer. This is also why adding the extra tall complete vertical strips sprites logic was really quite a simple thing to do, because just turning off that vertical comparator meant that it just kept on rendering sprite data, and all of the rest of the logic internally was all aligned already with basically having your 16-bit, having your 4-bit 0 to 15 value inside the sprite cycling round perfectly well, because it was subtly dealing with all of this extra logic anyway, or extra desire to render 32 vertical pixel sprites anyway. So that's why it was set up like that. However, the hardware wasn't allowing all of the sprites to be 32 pixels wide. That's why this is only set up to use the 4 bits for these indexes. There's also the Sprite enable or disable, so the hardware, by only setting 1 bit, can turn off the entire Sprite plane. This was added by me because I wanted a nice, quick and easy way of turning off all of the Sprite the Sprite calculation still goes on, but the pixel output does not happen. There is no pixel test. And this means that during the visible portion of the screen, if I would write to the Sprite RAM registers, there would be contention because it's trying to read from the RAM as I'm writing to the RAM. And when it reads, it was reading all sorts of random data. It's not random data, it's actually data that exists on the memory bus at the precise point when I'm trying to write to the memory. So this contention was visible in the simulated video hardware as different colored pixels, not the Sprite data that I wanted to see. I realized that if I wanted to have an effect or make use of an effect called multiplexing, I needed a way of very simply switching off all of the Sprite update pixel logic until I was done doing writes to the Sprite register RAM during the screen time, and then enabling the sprites again after I've finished. So that's why I added this little piece of extra functionality here. It means that it just outputs transparent pixels for each sprite, no matter what. And those transparent pixels then just don't get added to the scanline RAM. And that meant that I could add extra sprites. So the standard BombJack hardware has 24 16 by 16 pixel sprites. Using the multiplexing technique, I can render 48, 64 sprites, no problem at all, by updating the sprite registers as the screen goes down. The scan line moves down the screen, rather. So that, I think, covers all of the logic with the sprite on this part of the board. The next part of the board is the sprite logic part 2, which is page 5 on the PDF and root sheet 5 in the simulator. So this logic, first of all, I have a little digital data component here, which actually lets me record what goes in on 4C and 4D. 4C and 4D were the original scanline RAMs. I think I actually replaced it eventually with one RAM rather than having two RAMs. I wanted to have consistent RAMs, so you can see here on the schematic, this is actually enabled in the simulation and enabled on the PCB layout. The original 2114 RAMs, which are 4-bit RAMs, are excluded from the simulation. These 4-bit RAMs are really excellent, they're really nice and fast, but I just wanted to use these RAMs instead. I didn't want to have two chips, I just wanted one chip. So that's what I did. But I've kept it in the schematic just in case. So this logic here, there's this side for the first scanline RAM, and then this side for the second scanline RAM. The Sprite scanline logic is perhaps the most interesting part of the entire schematic, because it uses the entire 384 clocks of the horizontal pixel clock, of which 256 are visible, to calculate and write all of the potential maximum pixels for 24 sprites of 16 pixels wide. That's because 24 times 16 is 384. So we have two sides of the sprite board. One side is for the odd scan, and one side is for the even scan. And while one is outputting calculated pixels through to the output pixel header down here via these two demultiplexers, as you can see, depending on whether or not it's an odd or even scan line, it will choose the input from the left here and then output it to the right here, which then goes to the output pixel header. And these two inputs here will come from these outputs here for one scan line, and then the alternate scan line, the outputs come from here. So when the sprites are having their pixel data calculated, let's assume for the moment that, so these were the original 2114 RAMs, and I replaced it with one 6116. This just basically has 8 bits of data, whereas the original 2114s were set up to be 4 bits each. The 2114s are a little bit special, because if they are not writing, then they are reading. So, and they have a chip enabled, just like the 6116. So what this means is that let's assume that these RAMs, or this one, is filled with FF. The FF fill happens just after the calculated pixel data has been read from the RAM on the alternate cycle of the 6 MHz clock. It will first read, and then it will flip to a write enabled mode, and then just after its output a pixel down here, it will then use these weak pull-up resistors to then set FF back for writing back into the RAMs here, or because this is also connected to the same output, then the weak pull-up resistors will set FF back into this RAM and it will be written back. Because as you can see, either up here, 6 MHz clock is used to strobe the write enable, and the 6 MHz and the inverted 6 MHz clocks are used to strobe the output enable or write enable, respectively. So with these scanline RAMs filled with FF, what happens is this. For each sprite, the sprite index color X and Y pols are red, and that was on the previous root sheet form. After a successful Y-pos test with the vertical raster position, and with it being within 16 pixels, of course, unless the full screen height sprite flag is enabled, the sprite data counter is set, which is here. These are counters. These are alternatively used as the pixel position of the visible pixel if it's outputting, or it's set to the sprite X position if it's calculating sprite. And for 16 or 32 pixels, this will clock up. the data in the scanline RAM is first read. So either these two RAMs or just this one RAM, the data is first read when the inverted 6 MHz is 0. And the output value is then clocked. Okay, so the inverted 6 MHz here, when it's 0, output is enabled. Same here, the inverted 6 MHz, when it's low, the output is enabled. And what this means is that on the positive clock, as it transitions from 0 to 1, these two outputs will latch the value that has been read from the RAM, and it will then invert the read value from the RAM, and it will go to these outputs here. It's exactly the same on the other scan line, it's just that it's outputting to a whole bunch of different signals, but it's exactly the same logic on both scan lines, so we will only look at one. So this value here, first of all, loops back to the input here. Now these are two demultiplexers, and what happens is that the lower 3 bits, M0, M1 and M2, are passed through a 3 input NOR, and this basically says, or it asks the question, is the current contents of the scanline RAM transparent? If it is transparent, the value from the input pixel from the current sprite is output by these demultiplexers. And the output is also inverted and then written back into the RAMs. If it's not transparent, if the current data in the scanline RAM is not transparent, this means a previously calculated opaque sprite pixel exists at that particular coordinate. Then the value just read from the RAM is selected by these two demultiplexers, and it's written back. So this constant cycle of reading and writing of the RAM happens for every single pixel position on the scan line. And then at the end of the scan line, it will then start outputting the visible pixels. And when it's outputting the visible pixels, it will then cycle around again and start clearing the RAMs for the next odd or even scan line, depending on which side of the logic you're looking at. And then, as we saw, depending on if it's an odd or even scan line, it will then demultiplex and only output the one pixel to the pixel header. This logic is really efficient. It means that there isn't really much special detection logic needed, and the weak pull-ups help to reduce the complexity of the signals coming out or going into the RAMs. The RAMs will pull down from the weak pull-ups, so the values are not really affected. And of course, if the RAM is not outputting anything, then of course the pull-ups take over, and the pull-ups take over, and then the value is clocked here. If this is not outputting anything, if the output is not enabled, and the RAMs are enabled for writing the weak pull-ups, will pull the signals up, and then that's how the RAMs get filled with FF. So what it does mean is that these RAMs will be very sensitive to timing variation. I noticed this when I was trying to convert the board to be double horizontal resolution, or even just 50% more horizontal pixel resolution. The timing was extremely tight. So what I'm thinking is that if I really want to produce a better version of this hardware at some particular point with more horizontal pixel resolution, then I may have to have odd and even pixels inside. I may have to have odd and even pixels inside the scan to give enough time for the sprite rendering to finish its read or write cycle with these RAMs. Might have to do that, which would make things a lot more complicated again. The whole raster line schedule is actually documented fully in the Readme file. We can see, for example, when the full line starts at 180 horizontal pixel position and then goes to 002 FF. It gives us 384 pixel clocks per line. 256 of those pixel clocks are used for during the output phase of rendering pixels to the analog circuitry. However, all of the 384 horizontal pixel positions are used for calculating sprite data into the 256 pixels of the sprite scanline RAM. That's because, if you work it out, 24 times 16 is 384. That gives us our maximum fill rate, if you like. So blank in the scanline RAM is FF, and then values stamped into that, and then it's inverted on this way out, which is really, like I said, I think it's a really cool way of working. It's very, very efficient. It's also extremely taxing on the memory. These memory chips have to be extremely quick on flipping over between reading and writing. Luckily, they are really good at flipping over between reading and writing. If I remember rightly, because it's a 6 megahertz clock, you are talking about a 6 megahertz clock gives you up to, I think it's 166 nanoseconds worth of time to get everything done. All of the calculation, all of the logic, latching of the various values. And if you're going from reading the RAM to writing the RAM on a positive and negative cycle within 6 megahertz, then you have half of that for reading and then half of it for writing and clearing the values to FF. It's extremely taxing on the memory. When I was doing some experimental work on expanding this video hardware, where the horizontal resolution was expanded from 256 pixels to 512, I had to clock everything twice as fast horizontally. And whereas the character and the tile, and actually the Mode 7 screens were fine with this arrangement because their timing is less precise, the timing with the sprite update logic was so tight that actually it would not support 512 pixels. It would not support a horizontal clock at 12 megahertz for the pixels. I actually found that during my experimentations that even if I struck a nice balance in between, it didn't allow much more than 256 pixels horizontally anyway. So in the end I decided that I would shelve for the moment the plans to make the horizontal resolution of the display much better. It did look gorgeous with a higher horizontal resolution, but I couldn't really figure out at the time a way of getting all of the sprite logic to work properly. Then, following up actually on my work on the Mode 7 screen actually gave me some insights into using multiple pixel calculation paths. A little bit like the horizontal scanline interleaving method being used for the sprites currently. But it meant that not just on horizontal scanlines, but also on alternate pixels, I would be doubling up on all of the circuitry, which meant that I would be doubling up again on all the circuitry here and here. And I thought it was a little bit too much, to be honest, at that stage to start delving into that. But, you know, I haven't completely finalized the sprite board yet. I haven't ordered the parts, I haven't ordered the board, so I might go back and revisit this for the sprite board. It does mean that the video board that I've just built at this current time is obsolete. Anyway, so I probably won't. Version 4 of the hardware, I might look at making it horizontally wider in terms of pixel size, and maybe even more pixels vertically as well. It did mean that, say for example, the Sprite RAM registers, which are here on page 4, sorry, needed an extra register for the Sprite extra binary digit for the high byte for the 9 bits worth of data for the horizontal sprite position. And actually, I think I put it into the sprite flips and the sprite color, because I think at that stage I did not have a full screen height bit for the sprites, so I think I probably used this bit for the most significant bit of the sprite position. So anyway, that's the sprite scanline buffer hardware. Very, very interesting to see how it all works with all of the comparisons and everything else. Extremely interesting to finally get this working. In the original hardware, in the original schematic, there was a mistake, and that took a little bit of tracking down, and we'll get onto that later on. So this is page 6 from the original schematic. This is the root sheet 6 in the Proteus file. This is the character screen RAM and associated color screen logic. The character screen is relatively simple. We have the same arrangement of 3 planes, 3 bits for the character definition pixel, and we have the same arrangement for the flips. So depending on if it's horizontally flipped or not, it uses the same shifter mechanism that we saw in the sprite logic to decide whether or not to horizontally flip. And again, we have the same repeated pattern of 3 for the address selection logic going into the RAM, and this is whether or not to output the read information from the RAM, or to write the external data bus value to the RAM, and all of the associated RAM selection logic here and here. Address selectors, and again, the address for the character pixel data, which is 8 by 8 pixels, is again just a function of the character low bits followed by the character index. Because you're just using this as memory address, you're automatically multiplying up by 8 or by 16 in the case of the sprites, or by 32. You're automatically multiplying up by 8 just by shifting lower the character index and using that to address into the memory. So again, this is a very efficient way of addressing your character definition and your character pixels. The rest of this logic here is to deal with handling whether or not you are trying to write data into the character screen memory, or if you're trying to read data from the character screen memory. And the character screen memory also contains the color memory up in a different area of the memory, but it's all stored in the same RAM. So that's just using that signal here for RAM or color definition. And again, this decides on whether or not you're reading from the character screen or character RAM memory, and it's latching the value at the correct timed position. In this case, it's SL1 and SL2. SL1 and SL2 signals basically come from this little piece of logic here. And again, it uses the input for comp block and the horizontal pixel position, and it just switches these here. So you're reading RAM at the correct times, depending on horizontal clocked pixel position, and then latching it. And then using these values later on. This is just straight a latched character index. This is the latched color for the character. And again, this decides on whether or not you want to flip vertically or horizontally. If you're flipping vertically, flipping the character vertically rather, it just inverts the vertical pixel line to the lower 3 bits of the vertical pixel lines, because it's 0 to 7 or 7 to 0. And again, you're just shifting internally from least significant to most significant, or most significant to least significant, and you're just outputting the pixels that way for the horizontal and vertical flips. It's a really, really lovely way of doing it, really efficient. And then at the end of it, you just basically get the output pixel values here. Now, the character memory uses an extra 2 bits for the character index. This actually gives the bomb jack hardware the ability to not have just 256 characters. It doubles it and doubles it again. So you've got up to 1,024 characters with the palette lookup plus horizontal and vertical flips, which means that the character screen, because it has 1,024 characters, it doesn't use the full range of palette index lookups like the sprites and like the tiles can. So the character screen uses only up to a maximum of 128 colours instead of 256. That's kind of like an inbuilt limitation. because of these extra 2 lines here. If I wanted to reduce the number of characters that could be displayed, of course I could do that. And then I can use the extra line here for outputting extra palette index lookup. But I wanted to keep the number of characters that were available because the character data fits in these 8 kilobyte memories, right? So 8 kilobytes is 8,192 bytes. 8 bytes per character, because the characters are 8 pixels high. So 8192 divided by 8 is 1024, or 1024, which is 256 times 2 times 2. So all of this, binary maths, all of this shifting around of address lines really neatly gives you all of this, memory layout, and it really defines the memory layout in terms of byte data for the memory very conventionally. It was a relatively very easy format to actually figure out how to write conversion tools for. Very logical. So that's the character screen. Oops. That's the character screen. Very, comparatively speaking, very simple logic. That's why the character screen board is actually very small in comparison to the video board, which contains a whole bunch of extra analog circuitry here, and the output headers and stuff, and great big beefy stuff. We can actually visualize the output here, so we can see the output resistor ladders. We can see the output variable resistors for tweaking the video signal. We can see the big beefy blocks for the connectors here, great big nice beefy ones. So we can see quite easily the relative board sizes. So character screen. Next sheet down is the 16 by so page 7 on the PDF, on the original schematic PDF. Page 7 on the original schematic PDF. Root sheet 7 on the simulated schematic. Deals with 16 by 16 tile background picture logic. So the original bomb jack hardware would have a non-scrolling, so static screen, and it would enable you to select which game background screen you were rendering, and it would just, it would read the internally from ROM, it would read the tile definition, the palette, and then the tile pixel data, and it would just render a nice looking image. And there was a maximum number of tiles that you could have, and there was a maximum number of screens. I significantly expanded the hardware for the tile screen to make it accurately pixel scroll, but I also expanded the size of the tile screen so that instead of having I think it was up to 8 separate screens that were static, I made it so that it was one huge, large virtual screen that can be scrolled around in terms of not just pixel accuracy, but in terms of horizontal and vertical tile offset, with, for free basically, due to the address memory line, for free you could scroll it around and it would wrap around. This enabled me then to have a very large virtual 16 by 16 tile screen that I could very quickly scroll to any position I liked within reason, which is a lot more useful for scrolling games, which is why I added the whole feature. So similar to the character screen, but including all of the scrolling logic. These 74273s are used to latch various hardware register values for horizontal scrolling, vertical scrolling position, the lower 4 bits for pixel, and then the upper bits for character position, tile position, sorry. This here is for reading a static background color, and this static background color can be any of the 256 colors in the paleograms. This reads from the background internal data bus, BID. This basically reads the time. This logic here calculates new values for horizontal and vertical pixel values by adding the scroll to the horizontal and the Y pixel scroll to the vertical pixel position, and then outputting new internal values that are used by only the background. This means that only the background will be scrolling around. The character screen doesn't have addition logic here. This basically takes a 4-bit value and adds it to the 9 and 8-bit value for the horizontal and vertical pixel position. With the relevant carries, this accounts for the upper bits that need to carry through properly. So what we do is that then we have a virtual internal pixel position as well, which is the full 12 bits worth of accuracy. All of this extra accuracy is then used to adjust the positions that are looked up into for the tile pixelgrams, but it's also used to adjust the positions that are read for the. Okay, so this first block here contains the tile and color screen information. So this 8 kilobyte RAM is split up into two 4 kilobyte sections, which contains the tile, the huge virtual tile screen, and the huge virtual tile screen color map. The colors also, of course, contain the flip information, as you would expect. These next 3 then look up from the current tile index. They look up into the tile pixel memory, and they go through the same kind of shifters as you would expect to see. The tiles, although they're 16 by 16, still work on the internal 8 by 8 pixel model. So when it's rendering one tile, these will refresh 2 bytes worth of data for every 16 pixels that are output. The logic for horizontal and vertical flipping is the usual methodology that we would normally see. So the horizontal flips are either left or right shifted. The vertical flips, again, come in here, and whether or not it flips is based on some little bits of logic here, based on internally timed signals. This latches the color data. All of this logic is very efficient, quite compact really. Adding all of these extra adders did make things. Adding these extra latches for the internal scroll registers and adding the extra adders did add quite significantly to the size of the board, but then it's still medium size compared to the character realm. It's still in the middle of the Sprite board, so it wasn't too excessive. You can see here that this logic here decides on when it loads the different portions of the tile data, again based on the internally calculated horizontal position after applying the scroll. The demo arcade game actually makes full use of this huge virtual tile screen in terms of scrolling, because the whole RPG village style map is just one huge great big screen, and it just effortlessly scrolls around that just by updating a couple of registers. Okay, four registers. The background color is really interesting, because if the pixels are totally transparent, it then outputs basically color 0 for a tile. It outputs optionally the background color. The tile board itself does not decide on whether or not a tile pixel is transparent or not. Like the character board does not decide on whether or not a pixel is transparent. The only layer of the board that decides on whether or not pixels are transparent is the Sprite board, because it has the notion of having the Sprite buffer RAM for the scan line, and the Sprite horizontal position can render pixels anywhere within this scan line, so it needs to have that inbuilt way of having the transparent pixel test with the Sprite, because you could have all of the sprites bunched up on top of each other, so then you need the way of calculating whether or not which Sprite pixel has priority. The character and the tile layers do not do this test. All they do is just output the lower 3 bits from the 3-bit planes for the character or tile data, and they output the red palette index. So, but what does the final pixel combination of all of these layers is the next layer of the board. So the tile board has the ability to set at any point during the screen. There is no RAM contention or anything like that. It has the ability to set a full 8-bit pixel color and latch it at any point. This allows us to create a very fast way of updating the background color, and this updated background color information is output to pixel 4 header here. The original BombJack hardware had character screen, sprites, and tile screen. The fourth plane was basically background color and ignored. So I added the notion of having the configurable output pixel plane here. So the tile board can output its pixels, and it has the option, but it's not mandatory, that the other pixel header will output the background color. it's not it's not mandatory to connect this one up. It means, in theory, with 4 layers being calculated and combined together in the next board, that it means that we could have, say for example, 2 character screen layers, or 2 tile screen layers, or 2 sprite boards sandwiched together. If we had 2 sprite boards sandwiched together, that would give us double the number of sprites. If we had 2 tile layers sandwiched together, then we would have 2 independently scrolling, using independent graphics tile layers, and that would also be quite cool. It'd be nice for parallax scrolling and stuff like that. It means theoretically we could have 4 layers of sprite boards, and we could just have a sprite board piece of hardware. That would give us 24 times 4 sprites, which is a huge number of sprites, but it wouldn't cover the whole screen. That's why that's why we might want to have 3 sprite boards and 1 tile layer, for example. Or the combinations are varied depending on the type of game that we might want to do, which is a really cool thing. So the next board is Readme 8, which is page 8 on the PDF, and this contains the output pixel pipeline and palette lookup logic. What we have here is that we have some hardware so we have the headers, which take up to 4 layers of pixel input. Here, and here. And we have 3 pixel transparency tests, which uses the bottom 3 bits of the pixel from each of these headers. So 3 bits, 3 bit planes, up to 8 colors per character, sprite, or tile. This basically says, is it transparent? And it feeds in the logic levels into this selector here, and the selector will decide on which outputs to demultiplex. Basically, all of the pixel inputs come in here, and then only the chosen output pixel is provided for here. The reason why we have 3 tests here is because if all of the pixels are transparent, then by default we output the last layer, which in this case is the background color, but it might also be a tile screen, it might be a sprite screen, it might be whatever. It might be whatever we decide to plug into the 4th layer. I think on the original bomb jack hardware, it was color 0 all the time, I think. I think it was tied to one of the palette entries, and that was it. Okay. Then so in this schematic, I have these ones up here, and these ones are enabled in the simulation, but I also have kind of like these ghost ones here. So these are excluded from the PCB layer, and they are excluded from the simulation. But basically this block here, instead of having, instead of having character screen, sprite screen, tile screen, or instead of having, sprites, characters, tiles, it includes the mode 7 layer as an input. So we discard, so the mode 7 layer would take over the layer 4 pixel input here. So the mode 7 layer was put as a higher priority than the sprites and the background. And this is basically the configuration that can be enabled. So I would enable these here in the simulation. I would disable these in the simulation. I would then tell the simulation to read the test data output file, the debug signal output file from the emulation as it's running, and it would basically render the mode 7 layer on top of the sprites and the tiles, and it would show the almost exact same output as was in the emulation in the simulation for the RPG game. So that's why I've got these here. It's so I don't need to keep on remembering which ones to connect where and stuff like that to give me the different layer priority. So different layer priority is basically a case of, you know, unplugging and plugging in the pixel headers from different boards. You know, that's hardware configuration of layer priority and pixel priority for you. So the demultiplexed pixels then come through this logic here, and what this logic does is that it takes the pixels, it latches them, so actually the pixels start becoming delayed. So the addresses for the pixels are chosen. Say for example, we are rendering pixels and we are looking up pixel values into the planograms. So we are not writing data, so we do not select the address from the external memory bus. We use the pixel value itself, which is 3-bit planes plus 5 bits for the palette index. We use that to directly calculate the memory address into the 3 palette here. These are 4-bit output, and there are 3 2114s, and these serve perfectly well to store or retrieve palette data. I saw no real value at all, actually, in changing this to be a 6264, for example, because this allows 3 simultaneous reads of RGB data, 4 bits of RGB data. I did not want to have, you know, 2 6264s or 3 6264s. Right? There was just no need. This serves the need for reading and writing 4-bit palette data simultaneously perfectly well. These latch the external data bus, the external memory data bus values, but they don't latch it. They transceive the external data bus values onto the lines for the palette RAMs, depending on whether or not you're wanting to read or write to these palette RAMs. These two do latch the internal pixel information from the palette information. So 4 bits of RGB in each. These are perfectly adequate for latching 12 bits. And they latch them for the outputs. And then these eventually go to the resistor ladders. The original BombJack hardware resistor ladders were tweaked into this arrangement just because I wanted to make the color signals a little bit more stable compared to the resistor ladders that were used in the original hardware. The original hardware used a 2N net resistor arrangement, but I was reading up on this, and although it uses, I think, fewer resistors, it can be a little bit less accurate. This section of the board uses an updated resistor ladder arrangement compared to the board originally. I did redesign this to output more kind of like SCART levels. I wanted to make the output kind of definition a little bit more accurate, so I actually added the ability to tweak the output here with variable resistors. The voltmeter and the resistor here are actually not used in the schematic. They're actually not used, they're currently not enabled either in the simulation, because simulating analog electronics is very slow in a digital simulation. But when I was debugging this, I do have the option of enabling all of this, and then I can see, say for example, if I output all white pixels or all grey pixels of a certain value, then I can see that the appropriate voltage level is reflected here in this analog voltmeter. It's also here too. But the virtual digital display for the video signal reads in basically the digital RGB values. I did not write an analog decoder for this because I just don't want to go through all of that pain of creating an analog decoder for RGB values and then having a very slow simulation. So I just left it all digital, and I validate these by checking the voltage results. And you know, these resistor ladder arrangements do not change. So I just tested it once and then disabled it all for the simulation, but it's still obviously enabled for the PCB layout. This little piece of circuitry. Okay, so we have TP sync output calculation as well. Again, this is analog electronics, so I again excluded it from the simulation but enabled it for PCB layout. This section of the schematic deals with calculating on when we want to enable pixel output. Normally, pixel output is disabled during V blank and H blank periods. So we have no overscan because we don't want to, you don't want to output pixel data when you should be going through H blank or V blank. On old displays, there is a potential that you can damage the display by trying to overscan all of this too much. So it uses the vertical and the horizontal pixel positions with some comparators and some extra logic to decide on if it wants to use the X or Y borders, and whether or not we want to shrink or bring in or restore to default the borders of the screen. So horizontal and vertical border shrinkage is used to bring in the borders by 16 pixels, horizontally or vertically, or both in combination, to enable us to scroll the tile screen. So we can then pixel scroll the tile screen and introduce tiles in the area underneath the pulled in border. And I pull in the borders slightly depending on the values which are coming through the video header, and this I think eventually comes through the tile layer. That's where all of the logic happens for storing this, I think. And it takes all of these values and comparison results and border flags and the V blank and whether or not it's doing a compare block and so on and so forth. And then it basically decides on whether or not we are going to be outputting pixels with 1 pixel today. Because we're using a flip-flop and we're clocking it on the 6 MHz clock. So that's basically an overview of all of the original hardware, plus extension tweaks over and above the original hardware schematic. So the next layer is, the complex layer, which is the biggest board. So this board here has all of the pixel combination logic because it's the video generation board. Video signal generation board plus pixel combination logic sits here. So this last board is the Mode 7 board. The Mode 7 board is the biggest and most complicated and complex board. But it is not as timing critical as the Sprite board. So root sheet 9. Page 9 is doesn't have this in the original bomb jack hardware now, so now we're going completely off bomb jack schematic. This is new hardware. The Mode 7 calculation logic. This has register addressing. So this calculates which register 8-bit latch to enable based on the memory that I'm addressing. In terms of memory space, this is A00 onwards in hex. And these latches here then latch the information here. These are all 24-bit values that can be latched. 8, 16, 24 bits. 24-bit values get latched by this hardware. So with the Mode 7, there are 6 24-bit values that can be latched. There is also a last control register which decides on whether or not the Mode 7 layer is displaying anything at all, and whether or not the internal counters for X, XY, Y, and YX are held at 0, or if they are allowed to accumulate values internally. Mode 7 layer allows transformation, rotation, scaling, shearing, and flipping. This has the notion of internal registers, which every horizontal pixel and every vertical scan line will accumulate values for each clock. What this means is that you can have a horizontal pixel position with 24 bits of precision accumulating another 24-bit value. So that means that, say for example, every horizontal pixel you progress one horizontal pixel through the tile map, that means that you have no horizontal scaling. It means that there is no horizontal zoom or rotation or shearing or anything like that. So basically you are reading and writing one pixel at a time. But if you step half the amount and you have that accuracy built in because you have 8 bits of accuracy in the 24-bit value, then what that means is that you can have some degree of scaling. So you may read half the number of pixels, or a quarter, or a third, or twice, or 3, or 3.5, or whatever. And you can have this arrangement horizontally and vertically, and if you change the amount that you are accumulating on a per pixel basis as well, then you can change and you can skew the calculation as it goes through the pixel pipeline. So this allows you to introduce rotation, changing scales and stuff like that during the pixel calculation phase. So all of this logic here deals with accumulating these different values and latching these different values depending on your horizontal and vertical pixel position in the screen on a sequential per pixel basis or a per scanline basis. All of these accumulated values eventually come out into the various different registers for X and Y position. And these X and Y positions are then used in the next sheet. So root sheet 10 contains the logic that's necessary to decide on, based on a pixel lookup value into this large tile screen, it decides on the tile definition it wants to read. Data that's stored, tile pixel data that's stored, is actually stored on a byte per pixel basis. I did not want to have bit planes for the mode 7 screen because it would have made the circuitry a lot more difficult. So I sacrificed the number of mode 7 16 by 16 tiles. I sacrificed the number of tiles by reducing the number of tiles, but increasing the number of colors that you could have in the tile. So actually, each tile for the mode 7 screen is 16 by 16 pixels. 16 by 16 is 256 pixels, and each pixel is a byte. So I can have 256 individual colors within each tile. And also I have because that gives me a reduced number of tiles, I then use the upper spare bits for the tile index into the tile index screen for horizontal and vertical flips. So it all works out in the end that I just have one large virtual tile screen for the tile index, and then all of the other maths works out where I can use the lower 4 bits for the X and Y tile position to then index into the tile RAM based on the tile index plus flips for the horizontal or vertical flips. So this is what this circuitry does. This is these two, you can think of them as pixel pipelines basically. Because there are 2 pixel pipelines, it means that on alternate pixels horizontally while rendering the screen, it's calculating and then outputting the pixels in an interleaved fashion. This means that with a 6 megahertz clock, it would have given us a maximum of 166 nanoseconds to calculate new virtual screen position coordinates from all of the 6 registers coming in and all of the, adding and subtracting and accumulating. It's 2's complement math, so adding is the same as subtracting if you have a 2's complement number, a negative number, right? So adding is the same as subtracting. So taking all of the time that all of this would have taken, plus the time needed to decode and read from the virtual tile screen to indexing the tile pixel data, was longer than 166 nanoseconds by quite a large margin. So that's why this is doubled up, and that's why the inputs for these 2 are alternated. So pixel 0, pixel 1 on this side. However, if I scroll down, it's pixel 1, pixel 0. So what this means is that while the first pixel pipeline is latching the upper bits, it discards the lower bits because they're just used for accuracy for the calculations. Fixed point integer maths. Basically, you discard the lower bits that you don't need when you're finally calculating the output, but you still keep on remembering those lower bits in terms of internally accumulating and stuff like that. That's why the adder circuitry on the previous plane is 24 bits, and this is why this is using only 12 bits. So it latches the incoming value, and if we are not writing to the virtual tile screen, then we use the internal value here to calculate the address. So we pass through the address, and we use that to pass into the tile screen. And then we read or write the information in the tile screen. So we read the tile screen from the calculated tile coordinates. The lower 4 bits for the X and Y position naturally, of course, then go into the tile pixel position X and Y. Okay. The flip bits, which come from the upper 2 bits of the tile index of the tile screen, are then used to optionally flip the X and Y coordinates. Again, we have external memory bus address logic decoding, or we use the internally calculated values then for selecting which of the 2 tile RAMs we want to use. Originally, I designed this so that it would only use one 8 kilobyte tile RAM, and this, gave me a limited number of tiles for the whole virtually large tile screen. So I doubled the RAM for the tile definitions, but it did mean that I had to introduce a little bit of extra complexity in terms of deciding which RAM I wanted to select for reading or writing the tile data. But eventually it then goes through to this demuxer here. So the output buses go through this demuxer here. It finally then latches the output 8-bit pixel here for the tile that is currently being rendered on the off cycle. And it goes to the output here. And what it means is that then this or this alternate being active for outputting the tile pixel for the mode 7 layer. And then this eventually then goes through this little piece of cascading logic, which then tests whether or not the pixel is transparent. If it's transparent, or if the mode 7 layer is not being displayed, then it chooses the color, and then it goes through this demuxer here, which either has the option of using the loaded background color as a latch. Okay, so this is the background color that's loaded from this signal here, which was from the I want to latch the data for a background color here, or the flags. Right. Flags are loaded by this latch. The background color is loaded by this latch. It's like the tile data background value logic, but in this case the test for transparency is done on the mode 7 board, because the mode 7 board, instead of being the background layer, is actually the background layer plus another latched register value for the background, because it's the 4th plane. Right? So this does a quick little transparency test. Transparency test is done here, but the output of that is used here to change whether or not the demuxer uses the calculated tile pixel color or the background pixel color, and then it goes and it gets latched finally into the output pixel latch here, which then goes to the header. So that's the mode 7 board. There's quite a lot of maths involved, but it's all relatively simple maths. The Readme file details the precise calculations that go on in terms of when all of these values are reset. It also details how, say for example, the output pixel position is based on dx times x plus dxy times y plus the x or and likewise for the y output position pixel, it's dy times y plus dyx times x plus y log, for example. This allows any pixel to be scaled or transformed or rotated or flipped. But it's all very linear maths. Here, this is the maths, and then this is the pixel. And with 2 pixel units, this effectively gives us, double the amount of time, which is 333 nanoseconds. So the adders take up their own amount of time. The address logic decoding, the tile index read, the flipping logic, the tile address logic selection here, the final tile RAM read, and the output pixel latching logic. Because there's 2, it all happens in less than 333 nanoseconds, comfortably. So that's why we only have 2 here. I did have the option for going into 4, but I realized that at the particular simulated clock speed of for a 60 Hertz NTSC style display, I did not need more than 2 pixel pipelines for the Mode 7 screen. And it's actually relatively easy to understand. Just flows from left to right. Boof, boof, boof. I imagine that when I build this, these rounds are going to get quite hot, but that's okay. They're designed to cope with that. So what does it look like when I use this software to simulate? So using the digital, virtual digital display, if I start the simulation here, it takes a while to compile the netlist. It loads various libraries. It's usually not this slow. It seems to be having a little bit of problem. It's probably because it's quite late and my machine's starting to do an update in the background or something. But you can see that there's quite a lot on the screen. This is because the test data input enables all sorts of stuff. It enables the sprites in very silly positions. It enables all sorts of data in the character screen. You can see that it takes a good few seconds to render each complete screen. So part of this debug output for this display actually starts to output individual frames. Excuse me. Yeah, output individual frames to the output directory. So we can see this takes a while to render the frames, but part of the advantage for this visualization is that it outputs every single completed frame to a new BMP file. So then that's what I use to then, with Image Magic, to take the BMPs and then I convert it into like an animated GIF or whatever. But we can see that the simulation is simulating all of the sprite movement, including these full screen sprites here. There's some copper bars going on in the background of the Mode 7 there. We can see that there is a raster split here going on in terms of the bottom part of the tile screen actually scrolls at different rates compared to the top. And actually I can update the scroll registers for the tile screen at any point during the screen, so I can have 3, 4, 8 horizontally and vertically proportioned screens. If I use precise horizontal pixel timing in terms of like a copper list, then actually I can have horizontal and vertically split screens in terms of screen scroll. I can do similar things as well with the Mode 7 registers by exploiting the fact that I can reset the internal counters independently as well, and I can force them to 0 independently as well, which also gives me a whole range of extra intriguing effects based on, per pixel horizontally or vertical raster position as well. So in this test data demo, I use some, I think it's C++ code to calculate all of these, values for the sprite definitions and how they move. And actually I use the digital data generator to latch on the horizontal and vertical pixel positions. Also I use the v-blank latch to finally control when I can update all of these hardware registers. So now I'm demonstrating that the hardware very comfortably renders 24 sprites up here and renders another 24 sprites down here using the multiplexing technique, where up here in the v-blank, actually down here I think, just in the off-screen part, it sets the sprite registers for the top half of the screen, and then as this raster line goes down, when it hits this position, it switches off the sprites. You can see that the sprites are starting to switch off here. It switches them off. It updates the sprite hardware registers during this period. It then enables the sprite hardware output again, and then the new sprites using the new positions are then redrawn here. So actually the sprites down here are the same sprites as up here, it's just that they're using different definitions and different positions. And then this timing goes on, so every single frame it's updating the new positions here for the next frame, and then down here it's updating new positions. So very easily getting 48 sprites here. And this technique can be exploited to increase the number of sprites dramatically, at the expense of having more precise timing control. But the copper interface board that I'm planning basically emulates the fine horizontal and vertical pixel position and memory write timings as the digital data generation here. So the copper board will be able to produce horizontal and vertical copper bars. So here there's a little wavy line, and there's a similar wavy line here, and that wavy line is based on triggering the background color right at a precise horizontal and vertical pixel position as it traverses horizontally and vertically down on the virtual display, which gives us a whole bunch of really cool effects that would look really nice and really pushes the hardware way beyond what the original BombJack arcade hardware was doing. The original BombJack arcade hardware did have quite a lot of features. It would automatically do sprite multiplexing if you updated the hardware registers at the right time. It's just that you would see RAM contention issues because you would be updating the sprite registers at the time when it was trying to read them. So that's why I added all of this extra logic to add all of the blanking periods and all of the background logic, color changes and everything else, to really push the idea that you could use quite old 74 series logic to generate really quite complex visual effects, but still with a retro feel to them. That's the whole schematic explained. More details are in Readme file. And also the to-do and done text files also contain a lot more details about, especially the done file. It contains a lot more details about the series of modifications that I made from the original schematic to the version 3 boards, and beyond, depending on when you're listening or watching this. So thank you for listening. It's a very long recording and presentation. I'm going to split this up into several episodes, I expect. It's been illuminating working on this, and I'm still working on this and still constructing the boards. They're very expensive. The parts cost quite a lot individually, and then the boards in small quantities cost quite a lot to order, even though they come from China. I used a company from China that I'm very, very happy with. Their customer service was excellent. I'll be posting links to that company as well in the comments, in the description, and also in the Readme file you can see the company details as well that I contacted. The board worked, the video generation board worked first time when I was soldering it up and testing it. I think it's because I took a conservative route when constructing the board. I used sockets instead of soldering components directly to the board. I would solder the sockets and then put components in the sockets. All of the components for the ICs, all of the sockets rather for the ICs, have decoupling capacitors, which helps with the board stability. It means that I do not need to populate capacitors on the board myself. It's part of the socket, which simplified construction in some way and simplified the board layout as well. But the board itself, the components are expensive. The sockets are expensive because they're all gold-plated pins. With decoupling capacitors, they're not that common. The board itself is relatively expensive because the board itself is quite large and 6 layers. And then there's the time taken by me to do all of the soldering and testing and the plugging ICs and stuff like that. So no wonder these boards, when they came out in the arcades, no wonder they were very expensive. Because the original BOMJet boards were, for the most part, by the looks of it, the schematic was definitely hand-drawn in the PDF file. The layout for the board, the layout for the tracks and the components looks like it was mostly done by hand. The debugging, without this kind of simulation software, the debugging of this would have been horrendous. I can imagine lots of iterations of prototyping, breadboards and prototype PCBs and all sorts. So the amount of effort and toil that went into the original boards was phenomenal. My construction of this and my re-engineering and improving by introducing RAM and scrolling and extra sprites and mode 7 and stuff, my time and effort has been greatly simplified by having this Proteus simulation software. The Proteus simulation software not only does the schematic, but it also does the PCB layout. It does automatic placement. It does automatic routing, and it does a very, very good job. And the output files it generates are industry standard files that I just had to export them from Proteus and email them to the PCB manufacturer from China, and they just sent me back completed PCBs within a few days, even during the COVID pandemic. So all in all, modern software tools like this, like Proteus, really do pay for themselves, because I can do all of my simulation on this board, in this simulation software. I can debug all of the timing in the simulation software. I can, each of the memory chips and everything is configurable with nanosecond timing, and I can tell Proteus whether or not I think the RAM has to be fast or slow or whatever, and I can search for the bits on my router, and I can verify that the RAMs have this timing, etc., etc. And it will, the Proteus software will tell me if the RAM writing speed or writing frequency is too low, or too high rather, so that it will tell me, or too short. It will tell me if the writing speed for the RAM, or the attempted writing speed of the RAM, is too short. Too short RAM reads will very easily be displayed in terms of visual artifacts. The simulation is very stable. The simulation is not fast, but then again, I'm simulating a lot of components and a lot of pins. I don't expect it to be that fast, to be honest, and it's perfectly usable. If I want to do a long test, then I'll just leave it running like this, and I'll leave it running for a few hours, and then I will check the output results. So I can use this software to very good effect. I'm very, very happy with it. That's why I did this whole presentation on how the software is.